if G the compact group, then G admits a faithful representation is finite dimension. This is almost immediate consequence of the Petrov theorem, because Petrov theorem will tell you that there is sufficiently many finite dimensional representations, and then you have to add a little bit to say that there is a neighborhood identity which has no torsion elements, no element of finite order other than the identity. There is a neighborhood set. Once you have those two facts, this will follow easily. So this is a fact which I mentioned early on, and one consequence of this fact is following. So to fix the representation rho from G to G and B, let's say G and FC for some time. Faithful representation. And then this, of course, induces a really a homomorphism G into M and C. So then it has homomorphisms of C. Now, this rho dot, rho is a G into G and C, and you can actually do one thing. You can actually maybe go into G and R, and then you take the corresponding mapping of G to M and C. Then, you can take the map of rho dot to M and R. This extends, and this is injective, and this extends to an injective map, which I write rho C dot of GC, which is the same thing as G tensor C over R into M and C. And this is also injective. This is as a distribution. Since I put it into M and R, it follows that this is going to be injective. Because M and C is nothing but M and R tensors. So you have, because of this inclusion of G in M and R, which in turn is contained in M and C. This is contained in GC, and rho dot C is also injected. So corresponding complex bipartite algebra is a subalgebra of M and C, and therefore you get a complex subalgebra of this, and therefore you get a complex use of group of G and C. Get complex use of group, connected complex use of G and C, which I denote GC. GC is the complexification of G. And it's then easy to see that representations, finite dimensional representations, G are in bijective correspondence. Those bijective correspondence with holomorphic representations. Of GC. It requires a little bit of work. The point is that representation of G induces a representation of the Lie graph, and therefore we get a representation of the complex Lie graph, and therefore the corresponding separator complex Lie. But then the point is that if you look at the inclusion of G sits inside GC, and we know the fundamental group is this is finite, so you get the G tilde with finite group here. It's a finite cover, and clearly, if you take this cover of this, you automatically this lifts the map like this. Using this complicated diagram, it's quite easy. You get the same finite cover here, and using this complicated diagram, you find that representations of G are the same as representations of GC. Holomorphic and relevant representations by bisection correspondence. So the entire, in any case, it's clear that representations of G or GC on in G and P are in bisection correspondence with representations the point is that if you take representation of G, you can extend to GC. If you have a representation OC, you can try to extend to GC by simply looking at this as something present in C. So you really get a map of, if you B is a complex vector space, you get a map of B tensor C, representation of B tensor C. B tensor C, B is a complex vector space, breaks up into two parts. The subspace, the complex subspace, and its conjugate. Because the C, there's the conjugation which will get transported to B tensor C, and therefore the space will usually break up into two. But you can one of them you will get a holomorphic representation of GC, if you like. On the other, you will get anti-holomorphic representation. The bar. So that's why, but you can pick the representation which corresponds to the holomorphic thing, and that is what is the bisection response.
Can you explain this thing once more?
Sorry?
Can you explain this thing once more?
No, the point is that when you start with a complex representation, when you tensor it, see, you get, for GC you get two representations. The representation at its bar, you choose one of them
Yes.
to get a bisection response. That's all I'm saying.
So one of them will be one of the
The thing is that one will correspond to the complex linear map, and another will complex antilinear, conjugate linear map. So the thing will, you get a bisection corresponding to represent GLB of G on GLB, and representation GC on GLB. As we varies, of course.
So for this, are you starting with a complex representation and tensing with C?
Sorry?
You're starting with a complex representation and tensing with C.
No, the point is to start with the representation of G, but if you put it in a complex vector space,
So you put it in a complex vector space and then
the representation of complex vector space, then a priori you will get a canonical thing in G tensor B on B tensor C. G tensor C on B tensor C. But B tensor C breaks up into two parts. That's all I'm saying. And you have to choose the one in which the mapping becomes linear, the other in which it becomes antilinear. So you choose the right one. That's all I'm saying. I mean, sometimes when making a fuss of this, you confuse issues rather than clarify issues. Okay, so now the problem of finite dimensional, classifying finite dimensional representations of a compact group is converted completely into a problem of representation. It's clear. Compact semi-simple group, so that here. So from now on, I want to concentrate on the real representations, and we also work on for the group for finite dimensional representation. Because in the compact group, we know all irreducible representations are finite dimensional. So we want to classify. So the problem is there to classify finite finite dimensional representations. Of a semi-simple complex reality. And last time we saw that GC as a natural, as a since it comes from a compact group, so we also know from Wales theorem that every GC, every complex semi-simple algebra is the complexification of the real algebra, the real algebra of a compact, simply connected semi-simple liquid. We know all this. We know. Start. So you can actually forget the compact algebra altogether, but we don't have to because we know everything does come from a compact algebra. This is essentially due to Wales theorem. I mentioned the Wales theorem, but I did not prove it. Wales theorem, so too complicated to prove. In any case, to prove it, I'll have to say much more. I'm going to say some of it, but not everything that is needed. Because when I describe group systems, that's what goes into Wales proof. I'm going to talk about group systems now. That's it. So we saw also last time that G complex semi-simple GC. There exists. Sorry. There exists a abelian subalgebra, abelian real subalgebra, so called T, with the following properties. T with TC with the C linear span of T, then TC is the maximal abelian subalgebra. GC such that for every H in GC, add H. It's a semi-simple endomorphism. Of GC, so that GC that break eigenspaces. The semi-simple endomorphism means it's diagonalized. Add H is diagonalizable, which means the whole space breaks up into eigenspaces for TC. So that GC becomes the direct sum of TC plus alpha and phi G alpha. I hope we used the same notation last time, where phi necessarily finite set of linear forms, non-zero linear forms on G on these. Moreover, this is how it decomposes, and TC itself is the eigenspace corresponding to zero in TC star. Each of these alpha are linear forms on TC, and G alpha is the following: is a set of vectors P in G, C such that and H on P, which is something as bracket HP, equals alpha H. So each of these spaces G alpha is an eigenspace for H corresponding to the linear form alpha. No, you have an eigenspace with the whole of H, automatically get a linear form on H on this. And so this is what characterizes the. So the G alpha is in phi. It's a subset of. Is a finite set of linear forms. Which is already clear. The set phi is called a set of roots. The element alpha in phi is a root of G with respect to PC. I will generally omit saying with respect to TC. It's understood when I talk of roots, it's always with respect to TC. And the root is a linear form such that because such that it's an eigenform for the action of TC on G. And okay, and also and TC is precisely zero eigenform, otherwise the centralizer of TC is equal to TC, that follows from the fact it's maximal ability. If there's one more vector that commutes with TC, you can add it on and you will get a bigger. So, and if rho is a representation, finite dimensional representation, it turns out that and H is in TC, then rho H is sensible. This follows from the fact that if you the representation rho integrates with I call it rho dot on so that rho is reserved for the group. So if I take the corresponding representation of the compact simply connected group, which always exists given this group, then I know the torus acts, the elements of the torus act simply. It all breaks up into characters. With eigenspaces of the torus which are all characters. With the characters which are eigencharacters. And therefore, the corresponding Lie algebra, which is what I call the T, acts simply. And therefore, TC acts simply. So, all of TC acts, every element in TC acts simply. Simply, which means rho dot H is simply for every H in TC. So, it follows that. Follows that the B go the representation space of G is a GC is a direct sum of eigenspaces eigenspaces for rho of E. So V rho breaks up into some lambda. I don't know if I used the same notation last time, but let me. I don't remember what notation I used yesterday. But let me write simply just rho, depending on rho. Lambda is a bunch of linear forms. V rho lambda, where V rho lambda equals set of vectors at V rho such that rho dot h on V is lambda of h times every V rho lambda is a eigenvector with the same eigenvalue lambda. So it brings up to this. The S rho is a set of weights of. So there also all these are also linear forms. They are called weights of rho. Zero can be a weight, but zero cannot be a root because of conventions. So the weights of, if you like, rest of the adjoint representation at is same as P union 0. So add on 0 to get all the weights. So while 0 can be a weight, it's not a root by definition. Okay, now I'm going to introduce an order on which R over R. Recall that H is I times T. That's it for us. We know the eigenvalues of IT, the regular representation, are purely imaginary because they come from the torus, compact torus. It follows that all the eigenvalues of H, which are written down here, are going to be real. All eigenvalues of any x and h are in any representation are real. Now it's clear that h plus I times h, which is nothing but it here, is nothing but e here, and this is it. So this same as this, which is same as this. And every real linear form on H obviously extends to a complex linear form in H plus IH. And if you take a complex linear form which happens to be real on H, this complex linear form comes from the real linear form on H. So in some sense you can think of H star is hope by hope first H star and TC star is hope TC comma C over C. If I look at these roots and there's a natural identification, H star tells us over C, sorry, tells us over R of C with TC star. So I will regard, I therefore think of real linear forms on H as same thing as complex linear forms on TC, which take real values on H. You have a natural inclusion. So I will treat linear forms on X star, it's linear forms on X as linear forms on TC star as well. TC as well.
This T star lower subscript C.
Sorry?
The lower subscript C and the upper subscript C are the same thing, right?
So where did I put the lower suffix? I'm sorry.
Yeah.
Here, yes.
Oh yeah, it should be.
There is C.
Yeah. I'd like you to make such mistake often. So probably it's best to learn to ignore them rather than make me correct it here. Okay, so now the reason for looking at X star or X for that matter is the fact that there are their vector spaces and one the total order on X and X star. I will tell you how to introduce an order on X star. What you do is the model. Fix an ordered basis H1, H2, HL of H over R. Fix that once for all. An ordered basis. And I will say the form alpha in star. Take two forms beta, alpha, beta, and star. We say that alpha is greater than beta if the first non-vanishing difference alpha hi minus beta hi is greater than zero. That's it. And it's alpha is greater than beta. Is strictly different. That's an order which we define on the set of all linear forms, real linear forms. You do it on any real vector space once you choose a basis. Of course, it depends on the basis. This is usually called lexicographic order. Okay, with this notion of order on the real vector star, in particular, we get an order on set of roots, on set of weights, because they're all linear forms. And therefore, we can talk of the highest weight of any representation. So, finite set of linear forms, it always has a highest one. So, it gets linearly ordered. It's a totally ordered system, so you can always talk of the. So, one can talk of the highest weight representation of a finite dimensional representation. One can talk of positive roots, negative roots, or positive weights, negative weights. And so on. In particular, since roots are also weights, in particular, we talk of roots, positive roots and negative roots. So, let me denote by, I fix this ordinary once and for all, and I denote by phi plus the set of roots phi such that alpha is greater than 0. Notice that any non-zero linear form is either positive or negative. But some except must be non-zero. So this is the set of and p minus, right? P minus is a set of negative roots, P plus is a set of positive roots. We do this number of interesting things happen. First, I want to denote the probably used different notation last time, but I want to do it for it. I want to denote the BG. I want to drop the superscript C. So the news is coming in the way, so I'll drop it. BG. G is now on GC. BG is the killing form. Okay, I just skip this. I don't know. The killing form of GC. That is, it's the form BGC of XY equals base at X at Y. Killing was a German mathematician. It's unfortunate that the name means something in English. When I first came across the name, of course, I was amused that there's a name like that. Once it was very clear that it was the German, made no sense. Anyway, BTC is the base at X and Y. It's a bilinear, symmetric bilinear form. And we know, since G is M2, this is not degenerate. BTC is not degenerate. It is so-called Kappa theorem tells you that BGC is not degenerate. Now, I'll also abbreviate this BTC by this. Like what we do for inner products. Sometimes it's like inner product, except that our usual inner products are mostly different. It's not the case. These are complex here. So, complex by the forms. Now, the number things follow. If alpha, beta are both positive groups, so something like this. If alpha, beta are groups, then xy is 0 for x in G alpha, y in G beta, unless beta equals minus alpha. In particular, if alpha is root, minus alpha has to be root, because the form is not degenerate. Should also say that. Also, xy is 0. Also, if x is in G alpha and y is in but in the case of Mendelian form, the various root spaces are orthogonal to each other, except that the root space G alpha, the eigenspaces are called root spaces. So the root space G alpha is going to orthogonal to every other root space other than G minus alpha. And the non-degeneration therefore shows that G alpha and G minus alpha have to be pair non-degenerate. So this implies, first of all, since the whole G is a direct sum of the root space and H, from this it shows, this implies that if alpha is a root, so is minus alpha. And the bilinear form BG restricted to subspace G alpha plus G minus alpha. G alpha and G minus alpha is necessarily a direct sum because the intersection is 0. You can't have an eigenvector for the eigenspace alpha and common eigenvector for alpha and minus alpha. You cannot have alpha since alpha is not 0. So Vg restricted to alpha is not degenerate. That is clear from the fact, from this fact. See, form is not degenerate. If you look at G alpha, G1 alpha is not a root. The element X will be orthogonal infinity. Element in the element. G alpha is orthogonal to itself. Notice that xy is 0. If both xy are in G alpha. So that's the first statement. Now, second statement I want to make is that if X is in G alpha, Y is in G beta, then if you look at bracket X, Y, this belongs to G alpha plus beta. Now, this means the following: if alpha plus beta is not a root, if alpha plus beta is not equal to 0 and not a root, by this I mean that bracket X is 0. It belongs the eigenspace corresponding to alpha plus beta. The eigenspace doesn't exist, it's 0. Because if alpha plus beta is not a root, by definition of a root. So if alpha, this is what I mean by this, that is, if alpha plus beta is a root, oh, I should be careful. Yeah. What I mean by this is, if alpha plus beta is a root, is not a root, and not 0, then bracket xy is 0. What happens is this: if X is in G alpha and Y is in G beta, the bracket xy, whatever it is, has to lie in the eigenspace alpha plus beta. It turns out like H bracket with bracket xy. So it is Jacobi identity, it's nothing but bracket xx y plus bracket x xy. This is so-called Jacobi identity for here as well. Now, clearly this is alpha h bracket xy, and this is obviously minus bracket right hxy. Yeah, this becomes minus xh. Xh is sorry
Plus beta h.
Plus beta h of x.
not looking at that. So this is what hy is beta, so x beta h y. Yeah, this plus this plus this, and that gives you alpha h plus beta h. This beta h goes up into brackets. So brackets y is an eigenvector corresponding to this linear form alpha plus beta. And if alpha plus beta is not a root, there is no eigenvector of that kind, so that becomes 0. And but if alpha plus beta is equal to 0, one cannot conclude that the bracket is 0. What happens is this: belong to the eigenspace of alpha plus beta, which is 0, eigenspace corresponding to 0, which is nothing but Tc, what I call Tc. So what happens is this. If X is in G alpha and Y is in G minus alpha, terms of the you can bracket X y. This becomes equal to an element, yeah, this is the element in, actually, yeah, this is the element in Tc, because it belongs to the eigenspace corresponding to 0, which is Tc. On the same argument, it belongs to the eigenspace corresponding to Tc, so which is precisely eigenspace corresponds to 0 for Tc, precisely Tc, by what we already said. The real decomposes to the eigenspace for Tc, namely 0 eigenspace plus the eigenspace corresponding to every root, the direction of. So you find that this bracket X y in Tc. Further, the three form Vg restricted to Tc is non-degenerate. Why? Because we have seen that Tc is orthogonal to every root space. Tc is orthogonal. The argument shows that Tc is orthogonal to every root space. That is, you know that if X is in Tc and X is in G alpha, then Vg of Hx zero, because we know that X is in G alpha means it's going to be orthogonal to every eigenspace for Tc other than minus alpha, and Tc is an eigenspace corresponding to 0, which is not minus alpha. So this orthogonality persists. And once the dispute is over, what happens is you look at H, sorry, Tc, G is this, Tc plus rest sigma G alpha, alpha in phi, Gc alpha, alpha in phi. To do this, we know that this is entirely orthogonal to this. These two are mutually orthogonal. So in a restricted theory form, it has to be non-degenerate on each of these two pieces. Therefore, it's orthogonal to this. So VGC is non-degenerate from respect to Tc. And what's the consequence? This means this implies that for every alpha, every linear form, lambda in star in Tc star, there exists H lambda in Tc star such that lambda of H equals H lambda H in, this is the linear form, KV form. This is equal to lambda H for every H in Tc star. That's what non-degeneracy means. Non-degeneracy establishes an isomorphism between the vector space and its dual. And that's what I'm saying here. given any lambda, there is an H lambda. In other words, mapping TC star into TC given by lambda going to H lambda. It's nice one. See, if you fix, fix a element in TC, taking inner product with the element of every other element gives you linear form of the space.
You have taken H lambda.
Sorry?
H lambda comes to H lambda is an element of TCA.
So I see there's H lambda, this and lambda going to H lambda is an isomorphism, is what I'm saying. And H lambda is defined by this.
No, you
See, the facts that the mapping that the binary form is not defined assume that for any given lambda, there is an H lambda like this. So you get a natural map from lambda to H lambda. And this is my form.
That should be TC, not
Sorry?
TC star. H lambda. It should be TC. Second line.
Yeah,
Should be TC, not TC star.
given lambda, sorry, yeah, sorry, it's a TC. Yeah. So there's an H lambda in TC. Now the usual thing we do when you have a positive differential, the usual thing you convert every take the product of the given vector gives you linear form. That gives you an isomorphism of the original vector space in the form. Instead of doing it the positive differential form, I'm doing it for complex numbers where positive differential does not make sense, but non-degeneracy makes sense, and that's all you need to get this isomorphism. In particular, we have elements H alpha in a star corresponding to the roots. Sorry?
So you are identifying TC star with the TC by this binary.
Yeah.
Then you are identifying T star with
T star with, no, I should say TC star. It actually gives automatically an isomorphism. It turns out that this isomorphism gives an isomorphism of T star, which is from T bar, real with T and of H star on H. It's easy to verify that because we know that the linear forms, when we talk about linear forms on T, they take values in R, but our linear forms actually take values in I times R. But think of it as mappings in R, then you can identify T star with this, and you can write a small flow. T star with T and H star with T. Okay, now next we introduce an order which I have so far not said more about. I'm going to say something now. I will say let's finish the set of roots and P plus the set of positive roots. That is roots greater than. And we will talk about that because they will identify real linear forms on what I call H. So the elements of H star which is home H. We say the root alpha simple the root alpha is simple with respect to the lexicographic order we introduced. If it cannot be written as a sum of two positive roots, distinct positive roots.
So a positive root is simple, right?
Sorry?
A positive root is simple, not a root is
No, the root is simple if it's yeah. If it's positive and cannot be written as sum of two positive roots. I denote the delta to denote the set of simple roots. The point, just one point which I should have noted earlier. I'll come back to it later, but if alpha is a root and k is in R, psi is in R. Okay, psi is in R. It's such that psi alpha is also the root. If alpha is in P and the certain multiple of alpha is in P, then it implies psi equals plus or minus 1. If you have a root, only multiple of the root, where the only rational or real multiple of the root can be a root only if that real number by which you multiply is plus or minus 1. So only multiples of alpha are plus or minus 1. I'll come back to this proof. I forgot to look up the proof. I can't recall just now. But so this is a fact. And the second fact, which again I'll take up later, which is that dimension G alpha is 1. All the eigenspaces have dimension 1. So these are two lemmas which I will answer later.
that need not be true, right? I mean,
Sorry?
Psi can be half as well.
Half cannot be.
So if it's a
No, that can happen over a non-algebraic closed field. And we are talking about field of complex numbers all the time. So here, 2 alpha can be a root, but that happens only in the context of real algebras over other fields, not over complex numbers. Okay. These two lemmas I will postpone the proof to the next lecture. I want to say something more here. The next step I want to make for me. What is it? Yeah. Yeah. Set delta. Oh, no, second. Degree root is a linear combination of simple roots with coefficients of integers the same sign. All integers which are coefficients which are integers which are all greater than or equal to 0 or less than or equal to 0. Every positive group is an integral linear combination of simple roots with positive non-negative coefficients. That's what it means. And every negative root is a linear combination with negative coefficients, non-positive coefficients are the simple roots. Otherwise, if phi is in phi plus minus phi equals sigma m phi alpha let m alpha is delta is some rules such that m alpha phi greater than or equal to 0 m alpha phi less than or equal to 0. So it will be phi plus minus. What will do? Phi is in phi plus minus. If it's in plus, this holds. Minus phi minus this holds. So it's clearly enough to, since every negative root is minus of a positive root, enough to prove this for a positive root. This type. How do I prove it? Well, you start. This is a very easy thing because start with any root. Phi. If it's not the sum of two positive roots, delta. So if phi is not the sum of two positive roots, phi itself is in delta. And you are done. It's one of the alphas, so it's m alpha phi becomes the alpha. If not, phi becomes, say, phi prime and phi double prime. It's both positive. And induction takes over. Induction on the order where this root is placed. Okay, you start with the correct. You start with roots which are roots minimal in the order, then it tries to be simple because, and then an obvious induction happens. Okay. I think that's the point at which I'll stop. It's 1 hour, so I'll stop. My next lecture is tomorrow. So I'll continue next lecture. So, yeah, I should go. There's a step that there are. This amount to whether we take the book next time. And that is done with different one. Something about the group and when we the graph acceptance. We'll discuss next one time we'll discuss the real graph and the total representations. That holds the key to the. Thank you.